Hello, welcome back to iRender tutorial series. Today, we're going to explore a unique geometric structure called a rhombic spirallohedron. Russell Towle, 1949 to 2008, a Canadian computer specialist and geometry enthusiast, described an interesting surface which he called the spirallohedron. Towle proved that among the n-armed spirallohedra generated this way, those with n equals 3 and n equals 4 can tile space without gaps or overlaps. We can learn more about spirallohedron and their applications through scientific papers by Michel Petitjean and George Hart, introductory videos by Russell Towle, or tutorial videos by Junichiro Hanakawa using Houdini. But today, we'll recreate a version of the spirallohedron right inside Cinema 4D using the scene node system. Let's get started. We start with a node mesh, naming it according to today's topic, spirallohedron. First, we use a line node, axis is Y. Create a parameter to control the point count. Leave it as default at 30. In Michel Petitjean's report, we can use a formula to build our helical. The first thing is to create the theta angle. Use the geometry property get and iterate collection nodes to get the count and index information. Calculate the ratio and multiply it by the parameter with the value equals 2 pi. Create a parameter, named uParameter for later use. The result is the value of theta angle. We need the radius and height. Create the parameters R radius and H height to control them. Use the trigonometry and arithmetic nodes to build the x, y, and z values. Note that in C4D, the height axis is the y-axis. Use a compose vector 3D node to synthesize x, y, and z. Use geometry property set node to transform the original line into the required helical. An error occurred because we are leaving u parameter equals 0. Just set the value equals 1 to fix the error. Now you have a clean helical base. You can freely adjust a radius, height, or a point count to fine-tune the spiral shape. Let's build the core structure of our spirallohedron. Start by adding a transform geometry node. Create a parameter named kside to define the number of sides. We'll set the default to 3. This node will be used to rotate the base spiral around the y-axis by an angle of 2π/kside. Next, use a loft line node to connect the original spiral. And its rotated version, forming a base mesh. With the point count and kside parameters, you can now control the U and V divisions of this mesh for better resolution and detail. To construct the full spirallohedron, bring in a loop carried value node. Use a range node controlled by kside to determine the loop steps. Inside the loop, continue rotating the base mesh around the y-axis by the same 2π/kside angle for each iteration. Then connect the results. At this point, you'll see a clean spirallohedron with k equals 3. Try adjusting the kside parameter and watch how the shape evolves. Scientists have proven that spirallohedra with k equals 3, 4, or 6 can fill space without gaps. Let's test that theory with k equals 4. Start by creating a plane node. Use the existing R and K side parameters to control the length and width of the newly created plan segments. Next, use a distribution op node. Type as vertex and transform geometry node to distribute the spirallohedron on the points of the existing plane. Then, add another distribution op node set to polygon center, with another transform geometry node to fill the remaining spaces between grid points. We have clearly felt the space-filling properties of the spirallohedron. To explore its behavior in 3D space, continue with another distribution op and transform geometry setup. Then, keyframe the U parameter to animate the spiral's progression and see how the structure evolves dynamically. For the special cases of k equals 3 and k equals 6, we can construct regular triangular and hexagonal grid systems to test the same concept. You'll find that, once again, the shapes fit together seamlessly, clearly demonstrating the space-filling capability of the spirallohedron on both triangular and hexagonal tilings. This not only confirms Towle's findings, but also opens up possibilities for creative and efficient pattern generation in 3D design. And that's wrapped up for today's tutorial on the Rhombic Spirallohedron, using scene nodes in Cinema 4D. It's amazing how math and creativity can come together through nodes and visualization. We hope this video inspired you to explore more procedural techniques and try out your own variations. If you enjoyed the video, don't forget to like, subscribe, and stay updated with more tutorials coming your way. Thanks for watching, and as always, happy rendering, happy creating with iRender.